Good night, sir.
Yes. So you have the problem. I hope there is no difficulty in the theory that I explained yesterday.
No, sir.
You have any questions, you can ask. Okay, fine. So you can see the question here. The radius of a coil decreases steadily at the rate of 10 to the power of 12 meters per second. A constant and uniform magnetic field of induction 10 to the power of -3 Weber per meter square acts perpendicular to the coil. What will be the radius of the coil when the induced EMF is 1 microvolt? I hope you can solve this problem. Make the strategy. I don't want the solution. Make the strategy here. So make the appropriate drawings, and somebody who is confident, you please let me know the strategy. Please again let me remind you, it's a training session, it's a learning session. So I would like to know what you have learned so that I can teach you what you don't know. Just don't allow me to go on teaching whatever I know. Your time will be wasted. So please make the strategy and let me know what is the strategy that you have made. See, you must go through the fundamentals, then this problem can be solved. So they have asked you what will be the radius of the coil when the induced EMF is so and so. Okay, so from the given data, what you understand that the radius is decreasing means the area of the coil is decreasing. So here the quantities that you have to relate is the constant magnetic field, they have given radius of the coil, and you have to relate the EMF in the coil, isn't it? Hello?
Yes, sir.
So now, how these three things are interrelated? How these three things are interrelated? So basically you see E will be equal to minus d phi B by dt. That is the basic problem. Here they have told only one coil, so n is equal to 1. Here number of turns n is equal to 1. So in this case n is equal to 1. Now you attack this phi b. You attack this phi b. So what is phi b here? Phi b becomes what? B into A. Isn't it? In this case B is constant. So pull that B out, and what will be A? A will be pi r square. Okay, by dt. So this simply becomes B pi r out, d by dt of r square becomes 2r dr by dt. Correct? Correct now? Hello?
Yes, sir.
So you get this. So they have to, they are now, what are they asking? They are, what is the data that they have given? The radius of the coil is decreasing at this rate. So they are given dr by dt, and they are giving you B. They are asking you R. So here the quantity that you have to find out is R. So they have given this data, and this data they have given. That's it. And also this data they have given. So you know this data. This is it. That's it. That is the strategy to solve the problem, isn't it? It was not difficult. It was not at all difficult. See, I would like you to read the problem and see what are all the physical variables that are involved here. And in the first reading, second reading, you see they are telling the radius is, the area is decreasing. So then the only way that these things, so if area is decreasing, then the radius pi r square, so that mind should intuitively think, and then you will be able to calculate the radius. Correct? Okay. Now don't spend time solving the sum. If the strategy is right, let's move forward. Okay, so I have very good numericals I have collected to give you the conceptual clarity. Yes, so our strategy is correct. Okay? Yes. Okay, now go on to the next problem. Okay, the ends of a search coil. Search coil means a coil, okay, which is searching for magnetic field. Having 20 turns, area of cross section is so and so, and resistance of the coil is 2 ohms. Are connected to a ballistic galvanometer of resistance 400. Ballistic galvanometer means it responds to the maximum charge. Okay, usual galvanometer responds to the current, ballistic galvanometer responds to charge. That's the basic difference. Now, don't ask me about the construction and all. I don't want to get into the engineering details. Just understand it depends upon the charge. So, ballistic galvanometer raises. So, if the plane of the coil is inclined 30 degrees to the direction of the magnetic field of intensity so and so, coil is quickly pulled out of the field to a region of zero magnetic field. Calculate the charge passed through the galvanometer. Okay, just please read it and make the strategy.
Sir, ballistic galvanometer once again can explain, sir?
It depends upon the charge, maximum charge that is flowing at that time, not the current.
Okay, sir. Sir, but again, charge per unit time is current only.
Listen, I have given you now, don't get distracted and don't distract me. I have given you the data, you use that and start thinking. I will explain, don't worry. I am also solving the problem. So, as I see here, you keep doing it. Resistance of the coil is 2 ohms. Then ballistic galvanometer. I hope this is the data that they are given.
Yes, sir.
Yeah. Now the thing is, this is the arrangement of the thing, as you will see it at some time t, and what they are telling is this is suddenly pulled out of the magnetic field. No, it is in region of constant magnetic field 1.5 Webers per meter square. It is suddenly pulled out from there, and as it is suddenly pulled out from the zone, okay, a coil quickly pulled out of the field to a region of 0 and calculate the charge passed through the galvanometer. Calculate the charge passed through the galvanometer. That is the basic question. ठीक है? So from the given data, what happens when you pull the coil out? The flux linkages change. Correct? The flux linkages change. So what is the flux linkage? Flux linkage is N phi. So in this case, N into what is phi? Phi will be V into A into cos theta. Correct? Hello.
Yes, sir.
So this flux link, so this is the flux linkage to begin with.
Yes, sir.
To begin
Yes,
with, this is the flux linkage. Now, when you pull it out of the zone, then the B becomes 0. So it means this it comes out of the region suddenly. Have they given any time in there? Quickly pulled out of the region of 0 magnetic field, calculate the charge passed through the galvanometer. Okay. Think it over, how will you handle this?
EMF we can find, sir, by d phi by dt.
Do it. Make a strategy there, please, all of you. Sorry, I made a mistake. It is 30 degrees to the direction of the magnetic field. So this becomes 60 degrees. 30 degrees to the direction of magnetic field. So it is 60 degrees. Okay. I told you the ballistic galvanometer will depend on the charge. So you will get this. So now if you pull the coil out, what happens? You will have to calculate delta N phi. Correct?
Yes.
So
Yes.
delta N phi will be, you have to just plug in these values. What are the values here? 20 into B is 1.5, right, plus 3 by 2, and the area is 1 centimeter square. So I write it as 1 into 10 to the power of minus 4.
Minus 4.
And the cos theta is half. Okay? Okay, so here 2s are 5s are. Quickly goes.
15 into 10 raised to minus 4.
So you get here 15 into 10 to the power of minus 4. Okay, now units. Just write units and keep it there. If you want the final solution. Right. See, in PUC, in board examinations, you must write the units. Don't simply write. I am doing the rough work that you have to do during the mains and NEET examinations. But during board examination, you need to write the units. So this is delta phi. Okay. Now, I will now take this delta phi divided by delta t, because I don't know. They have told it will quickly come out, so I will divide it by delta t. Okay. So if I divide it by delta t, then I will get here what? The induced EMF.
Yes, sir. Yes, sir.
I will get the induced EMF from this. Now, induced EMF in the coil, I will get this induced EMF. But then, how much will be the current that will flow in the coil? For
We
this,
can use V equal to IISc into the resistance.
so you will divide it by the resistance.
Yes, yes, sir.
So you will divide both sides by resistance. So if you
Yes.
divide both sides by resistance, so I will divide this side by resistance, this by resistance, and this also by resistance. Okay, I will divide this by resistance.
Yes.
Okay. So what will I get here? If I divide it by resistance here, I am going to get this side E by R. I am going to get current I. Isn't it?
Yes. Yes.
So I get here current I is equal to 15 into 10 to the power of minus 4 units upon R, and I will take this delta T this side. So if I take this delta T this side, I will get Q. I will get Q.
Yes, sir.
So that is precisely what they have asked us to find out.
Okay, sir.
Okay? So they are giving the value of R. R what? this coil is having resistance of 2 and this is having 40. So you will take it as 42. Correct?
Yes, sir.
And,
Yes, sir.
and so 15 into 10 to the power of minus 4 divided by 42. So this will be the charge in coulombs you should get. Okay?
Yes.
Right.
Yes, sir.
So this is the broad strategy with which we should work, and let us see. I hope, see, you should be able to grapple this. See the way I have solved it. Whatever data they have given, I have just captured it and just drawn a schematic so that I will get to know the currents and etc. And then, you know, as I told you, ballistic will only measure the charge. So I don't know how to proceed. But I don't know, I really don't know. At this stage, I wrote this and they said you take out the coil instantly. Instantly means it will take some time. I don't know the time. So I just put it as delta T. So once I put it delta T, I get the EMF induced. They are given resistance. So I get current. So I will get current here. Then the moment I get current here, they want the charge. So therefore, this delta T which was created by us, an auxiliary variable. So I put it here again. So this is how you have to approach the problem. Okay, you should not start thinking, oh, Q, how it is related. No. Sometimes you see, if you simply follow the process of science, it will take you to the destiny. Okay, so that belief you should develop. That process you should develop. Okay, so your mind should start thinking in the direction of science. The process is science. So then automatically you will get. Because see, after writing this equation, I don't know, I also didn't know what to do. But then I remember what else can be done, this is what I can do. So then it will lead you to the solution. Anyway, let us see whether what we have done is right. Okay, he has directly written it, but anyway, we will also get the same answer. Okay? We got 15 into 10 to the power of minus 4 divided by 42. So 2 ones are 2 times.
Same result.
Same result. Okay, done. Now, don't sit and calculate. I'm telling you. You should focus on whatever I am telling you. So right now in the class, you are completely under my control, and you should just do what I am trying to tell you. So because there are wonderful problems that I have collected, so you will get a very clear conceptual clarity. Okay, and most of these questions were asked in the examination. Not only they were asked in the examinations, but it is also giving you conceptual clarity. I have adjusted those problems in such a manner that you get very good conceptual clarity. Okay, now this problem. You can see the problem here, students. Next one.
Yes.
Yes, sir. See, this is called primary. Means you are using an active source here. See, you see here, E is a battery that you are connecting here. This is the key and this is the rheostat. The moment you plug in the key, the current starts flowing here. So that is why this is called primary. So that means as soon as you close the key, the current starts flowing. Now, since the current starts flowing here, then the magnet, so this current flows, then it creates magnetic flux. This magnetic flux of this coil, is linking another set of coil, another coil. So therefore, whatever magnetic field is created by this, it will link another coil and it will induce EMF in this coil. Got it? So that is why this is called primary, this is called secondary. Is that clear?
Yes.
Now please solve this. Aram se solve. See, you follow the process of science. I am not interested if you get the right answer or wrong answer. I want to make sure that first and foremost thing, you are following the process of science. So please do that. When the resistance of the primary is changed according to the figure, then what is the induced current in the resistance R in the secondary? That means now here there is a rheostat. Can you see there is a rheostat here?
Yes, sir.
So here the voltage is fixed. E is fixed. Okay, and here by varying this, by moving this arrow, you are able to change the resistance. If you are able to change the resistance, you are able to change the current here. I suppose all of you know this.
Yes, sir.
Great.
Yes, sir.
Great. When the resistance of primary is changed according to the figure, that means now if you keep the rheostat point here, that means the resistance is 0, got it, of the circuit. And if you
Yes, sir.
keep pulling it to the right, then the resistance is increasing. I hope you understood.
Yes, sir.
That is what you have to be keen here. So that means now initially the current was high, now the current starts decreasing in this coil. Okay?
Yes, sir.
So now you look at the direction of the current. That is, if you see from this phase, whether this is north pole or south pole. So the current is going like this, in this phase. The current is going like this. So this becomes south pole or north pole? It becomes south
Yes,
pole.
sir.
South pole.
Yes, sir.
It becomes south pole.
South, sir.
First one will become north.
This, see my cursor is there, no, that one.
Yes, that one south pole.
South pole, got it? So this becomes south pole.
Yes, yes.
South pole means the flux is entering inside this. Hello?
Yes, sir.
The
Yes.
flux is entering inside this. Okay? The flux is entering inside this, and this flux is, see here, this flux is coming through this and entering this. You can understand? See, the flux lines will go like this, go here and come here. Did you understand what I told? If you didn't understand, I will
Yes, sir.
draw. You tell clearly, sir, we didn't understand, you draw. God has given me everything here. Wonderful board and etc., etc., etc. So I can do it for you. See, only thing is I am trying to conserve time. Okay, so if you say yes, no issue. So here you have a coil and here you have another coil. Okay, so I said the flux, this becomes south pole, so the flux is entering here, correct? But this has to go like this and come here, got it? Hello?
But if you look at the other phase, the flux will be leaving from that side.
From this side it is leaving, let it leave. What is your problem?
Okay, sir.
So why did you unnecessarily stop? And you see, you concentrate properly. Like say, definitely I am interested in what is happening here. So as far as what is happening in this part of the coil, what is happening? That's important. Okay. So now you look at this side of the coil. So you look at that side of the coil. Okay. So the flux is coming like this. Okay, coming like this in this coil. Correct? So from the side of a primary, if you are seeing the secondary coil, from the side of primary, if you are seeing the secondary coil, look at the direction of the winding. I hope you can understand the direction of the winding. The winding sense is in, see, my finger is moving like this. I am seeing from this side the secondary coil. So the winding sense is in anti-clockwise direction. Can you feel that?
Yes, sir.
The winding sense in the secondary, if you are seeing it from the end of the primary, it is in anti-clockwise direction. Okay? It is in anti-clockwise direction. Got it? And
Yes.
now the flux through this coil is in this direction, towards me.
Yes.
And
Yes,
the,
sir.
the coil is like this. The coil is like this.
Yes, sir.
The flux is towards me. Okay. Now the flux is towards me. Now flux is towards me. Now if you move this rheostat, this flux is reducing. This flux is reducing. Got it?
Sir, why do you need to only increase the resistance? You can also decrease it, sir. Your stat means variable.
ನೀನು ಏನಾಗೈತೋ ನಿನಗೆ ಅವರು ಕೇಳ್ಯಾರ ನೋಡಿ ಇದನ್ನ ಸರಿದ ಓದು ಅಜ when resistance of the primary is changed according to the figure. So according to the figure they have shown arrow also, no?
Yes, sir.
Then that means they are telling you, you go from here to here. You go from here to here, you increase the resistance, and as you are increasing the resistance, what happens? See, aram se read, man. Don't create that confusion in your mind like that. Understand? You be smoothly you understand. See, don't start thinking, oh, rheostat means both direction. Here, look at the diagram, it is very clear. Okay, then. So, see, I was explaining something, you interpreted. So, the coil sense is like this, and the field was coming like this. Now, you see here, the field is like this. So, if you move the rheostat from left to right, here, rheostat, then this flux is reducing. Hello, is that clear?
Yes, sir.
So this flux is reducing. Now here the current will flow in a direction to maintain the original flux. You got it?
Yes, sir.
To maintain the original flux. That means now if you see here in the secondary, to maintain means the current from this end should flow in anti-clockwise direction here. Got it? The current should flow in anti-clockwise direction in the secondary. Then what happens if it flows in anti-clockwise direction? Then it will create a flux towards me. Okay, because in the primary the flux is reducing. So, but what is Lenz's law? It doesn't want to change the flux. It wants to arrest the change of flux. So therefore, current will flow in this to aid the flux, and therefore it will flow in anti-clockwise direction. Therefore, in this resistance, the current will flow from left to right, L to N. Got it?
Yes, sir.
So, what is the direction of the induced current in the resistance? So it will go from L to N. That is the answer. I hope you got it.
Yes, sir.
If you have any confusion, ask. I will explain. Don't worry. See, you are all learning it for the first time, students. So if you say I don't know, nothing wrong. Nothing wrong. I will make it clear to you. See, you are all wonderful students. Nothing wrong. See, we are not Prahaspatis here. Nobody is intelligent here, including me. Okay, we are going to become intelligent by our efforts. So we are in the process. So therefore, let us be humble. Let us accept defeat wherever we have to accept defeat. And whenever we are successful, let us be humble. That's it. That is how your nature should be built up. And in your real life also, if you develop this nature, you will be very happy throughout your life. Okay, I hope I made myself clear to you.
Yes, sir.
Okay. Now you see the important thing. This current will flow to ensure that whatever flux was going before, it will not change. You remember Mr. Abhinav? Yesterday I had corrected you.
Yes, sir.
Yeah, into yeah is the answer. Correct. Okay? Let us proceed. See, we have to make sure our concepts are correct, our understanding is correct. That is the purpose of this class. Okay, now go with this question.
I think you got stuck, sir.
Over man, nothing. I was telling something. Now go to the next one. L2N is written here. Why? What is there to be stuck? The cross-sectional area of a closely wound coil. Please read this. So same like previous problem. Correct now? Ditto same like previous.
What is BGG?
Yes, sir. Yes.
BGG is ballistic element. Everything is same. 100% same. Only thing is the the numeric the values are okay. They are given 30 degrees and all. That problem was more complicated. Here it is percentage. So we don't have to do this problem. Same like that. Okay, go with this. Next one. A current I is equal to so and so. Into 10 to the power of minus 2 ಅಲ್ಲಿ into ಹೋಗಿರ್ತದಲ್ಲ ಇಲ್ಲೇ into 10 to the power of minus 2 amperes increases at a steady rate in a long string conductor because current is directly proportional to time. Okay, a small circular loop of radius has its plane parallel to the wire. Okay, parallel to the wire. A small circular loop of radius 10 has its plane parallel to the wire. Okay, and its center is placed at a distance of 1 meter from the wire. Okay, the resistance of the loop is 8.4 into 10 to the power minus 4 ohms. Find the magnitude of the direction of the induced current. So make a drawing of this, then I think you should be able to solve. So long straight conductor is there and the circular groove is there. The radius is say and its plane is parallel to the wire. Right? That's it. So if I draw the wire, long straight conductor like this, okay, and assume that this wire is on the plane of this board, and then parallel to this plane of board, I have a current flow. Okay?
Yes, sir.
So if you see from this side, you will see the wire and the loop. You will see the wire and the loop, and the distance between them is 1 meter. 1 meter or whatever it is.
1 meter.
1 meter. Okay. Then parallel to this, the resistance of the loop they have given. Okay. Then find the magnitude and direction of the current in the loop. So here they are given the value of the current in this one, and this distance is 1 meter, and the resistance of this loop they have given. They have given the resistance of this loop and this distance, say this distance d they have given. Okay, so how do you go about doing this? So the current is going in this wire. So now I hope you can imagine this. The current is going in this wire. And I am showing you the loop here. Loop from this end, you will see only a line. Correct? You will see only a line. So the current is going in the conductor, long straight conductor. The magnetic field will be encircling it. Correct now?
Yes, sir.
The magnetic field will be encircling it. So if the current is going like this, the magnetic field
anti-clockwise direction. Into the room.
So this side of the coil, it is going to come out.
Yes, sir.
This side of the coil, it is coming out.
Yes.
And in this side of the coil, it is going inside. Correct?
Yes, sir.
Correct now?
Yes, sir. Yes, sir. So let me number.
Wait a minute. Don't be in a hurry. So this is the conductor. So the magnetic field lines keeps on going here. See, now the aram setting. This, what I have written here, may be right or may be wrong. Then you simply don't say yes to that. You have to have a very good idea of the three-dimension activity here. So there is a plane here, the coil plane is here, conductor is here, then the magnetic field will be curling like this, and till it reaches 1 meter. So 1 meter, it touches the center of this coil. It is not off-centric. Well, just read it the problem. Now, a small circular loop of any side has its plane parallel to the wire. Has its plane parallel to the wire, and its center is at a distance of 1 meter from the wire. How will you understand this problem? See, if what I told, if you understand like that, that is, you have a coil in the front and you have the conductor here. I hope you are able to see what I am doing here. My finger and this. So if this is the arrangement, then the magnetic field will be simply going like this. And say, I mean, the magnetic fields are many circles, many concentric circles. Hello, are you with me?
Yes, sir.
So the first concentric circle will just touch the plane of the coil. Okay, but what happens? It touches and it enters and it comes off like this. See, what we are interested in, what magnetic field pierces through the coil. Hello, are you with me?
Yes, sir.
So now, if you see here, see now, you can understand that the curling is like this. The circles, if I draw around the current, are increasing in its radius. Okay, one such circle will just touch the plane of the coil, and then the immediate circles will enter from one end and come out of the other end. You see, it should go through. It should go through. So this arrangement will not give any current in the loop. Okay,
Yes,
but this problem is something to do. So therefore, our thinking may be wrong. Okay, so let us read the problem once again. Okay, a small circular loop of radius has its plane parallel to the wire, and its center is at a distance of 1 meter from the wire. Okay, so one interpretation of this sentence was like this. Now let us see the other interpretation of the sentence. What is the other interpretation? Let us have the conductor like this, and supposing I have the coil like this. So this is also same now. So the plane of the coil is parallel to the conductor, and the distance of the center is also 1 meter. So this is also going to show. In this case, you see the magnetic field on the right side of this. This side it is out of the ball, but this side it is into. So you have magnetic fields entering the loop and coming out of the loop. Correct now?
Yes, sir.
Yes, sir.
So therefore, there will be induced EMF in this. Okay?
Yes, sir.
So this makes sense. So let's see. A current of this, a steady current using a grade, a small circular loop of radius so and so as displayed the wire at the central resistance. The resistance of the loop is so and so. Find the magnitude and direction of the induced current in the loop. So therefore now you must now first find out what is the magnetic flux. See, assume that there is some current I going here. So assume a steady current I. If steady current I is going here, there will be magnetic field inside this. Correct?
Yes, sir.
But you see, the magnetic field here, here is different. Can you understand that? Why? The proximity of this. Bayes-Sauer's law. Hello, Bayes-Sauer's law. The magnitude will depend upon this distance r. The magnitude will depend upon this distance r. Correct?
Yes, sir.
So therefore now you have to get to know what is the magnetic field here due to the current I. What is the magnetic field inside this loop? Magnetic field is not going to be constant everywhere. Understood now? It is changing. So how will you go about?
So we can take Bayes-Sauer's law, sir, and we can differentiate it with respect to time.
Okay, you will see. If you say Bayes-Sauer's law, current I is there, and you will get magnetic field at some point here. Say if you want to know the magnetic field at this point at some distance x from here, you will get to know that.
Yes.
That is the magnetic field here, dB here. Supposing you take this distance as x, you take this distance as x, then you will get here what magnetic field mu naught by 4 pi I dl, okay, into sin theta divided by r square. This is what you are going to get here.
Yes, sir.
So this is what you will get at this point, right? But you would like to know the total magnetic flux here. Is it necessary?
Sir, the area vector and the magnetic field vector, sir, they are in same direction, sir. So we need not consider that
Again. See, okay, now that means now you don't mind the magnetic fields and all these points are different. Is it okay? You can still manage to handle that with whatever logic you have got?
Yes, sir. It's not distance varying, sir. It is time varying. So you can get the magnetic flux from that coil.
No. The magnetic flux is also distance varying. No. Don't you take that? Is it not necessary to take that into account? See, what I am trying to tell you, that here it is dB1, here it is dB2, here it is dB3, because it depends upon R.
Yes, sir. Yes, sir. Okay.
So what you have to do now here is, this is a circle, here you take a circle. So the magnetic field you have to find out for this incremental area. This incremental area from this conductor. You have to find out. All of you are thinking about the problem?
Yes, sir.
Sir, we can simply consider the flux as B into A, sir.
But
Area I have already given, sir.
No, why they have they given? Okay, I think Aniket is right. You are telling take the flux as B into A. Now
Yes,
Aniket is telling don't complicate it, because the flux at each point is different. B is different, okay? But Aniket is telling don't take it, sir, take B at the center as B and calculate the total flux B into A. On what basis are you telling, Mr. Aniket? That we can take it like that?
Sir, can we say that the radius is very small as compared to the 1 meter distance?
On what basis are you concluding like that? There should be some basis for you to conclude, no?
So, since the given radius is 10 to the power minus 3 meters.
Okay, but so you want to conclude, eh?
So, 10 to the power meters.
No. See, you are going to solve a very, very important examination in your life. Do it correctly, you will get 4 marks. Do it wrongly, you will get minus 2 marks. So, are you going to risk? Okay, fine. But your thinking is in the right direction. See there. They have written it there. You read the sentence very carefully. Current I increases at a steady rate now. A small circular loop. You see that word small?
Yes.
See, they could have, in physics, you know, there is no faltu words used. Understand? They will not use one word also faltu. No adverb, no adjectives, and no faltu words. If they have, they could have written a circular loop of radius. Correct? No? Why did they use small? So, small for us means, well, you can consider it is very small. So, that means now they are indicating to us that you can consider the magnetic field to be constant.
Yes, sir.
Understood? See, I am telling you, see, in examination, you know, this is where we have to be extremely careful. So, when you draw the diagram, oh, I am stuck with the problem. Okay, so how should I know? So, I don't know. So, then what you should do? You should once again read the problem once again carefully without becoming tense. So, once again, if you read, you will get some hint. You will get some hint. Small circular loop. Iska matlab hai, whatever magnetic field I calculate here, this into this area. That should give me the flux. Okay? Hello?
Yes, sir.
So my job is very simple. Okay? My job is simple. Okay? So therefore now, my job is, I have the conductor here. I have a small circular loop. And this center is, this center if you take B is equal to 1 meter. So I have to calculate the magnetic field at this point, B. So B at this point, you know, mu naught by 4 pi D into I, mu naught I by 4 pi D, isn't it? If this current is I. Hello, am I right?
2 pi D, sir.
2 pi D bartada? Okay. I don't remember. Are you sure it is 2 pi D? Yes, somebody is very confidently telling 2 pi D. I will go with it. So B is equal to so and so, correct? Now what we want is flux. So multiply it by area. Multiply this by area, correct? So multiply this by area pi r square. So they are given the radius of that loop. They are given the radius of this is pi r square. You get this here. Okay? Then our job is quite simple. Okay? Now current I increases at this rate. So to the wire and they are given the resistance of this loop. Okay. So from this, if I differentiate this with respect to time, I am going to get a rate of change of potential, isn't it? Rate of change of potential, dE by dt I am going to get. So dE by dt and I am going to get there. So here, so mu naught is constant. What did we do? So, mu naught is constant here, mu naught is constant, then pi r square is also constant, then 2 pi d is also constant. Now, only thing that is there is di by dt. Di by dt will be. Correct now?
Yes, sir.
So, what did I get here? I got the rate of change of potential induced in the coil.
So you indicate potentials.
Yes, sir. Not rate of change.
Oh, sorry. Thank you. Sorry. You will get the potential. Thank you. So you get this potential is equal to so it's di by dt. Then what else have they given the data here? Current I is given to you, so you can differentiate it and you will get di by dt. What is issue? Then they are given the resistance of the loop. Find the magnitude and direction of the induced current. So I give the resistance of the loop. So if you divide it by R, both sides. So you are going to get here what? You are going to get the current.
Yes, sir.
You are going to get the current. Okay, you are going to get the current. So and di by dt. So the equation is given. If you differentiate it, you will get di by dt. Substitute there, and then you are going to get the induced current. Okay?
Yes, sir.
Yes, sir.
Okay, fine. So, okay, let's see. We have done a lot of circles here. Correct. So what we have taken there is Pakka fact. Okay. Okay, B into A. So they have also taken that. Thank God. But they have done a lot of calculation here. Don't try to do all those calculation here. Induced EMF is so and so. They have got it. And I is equal to so and so. So di by dt they have calculated. Fine. And E is equal to so and so. And then induced current is by R. So don't do intermediate calculations here. Get the final formula, then plug in the values.
Yes, sir.
Then, so the direction of the induced current in the loop will be inverse of that of the wire. It will be in anti-clockwise direction. Right? Obviously, if this current is increasing, then the flux is increasing. So the flux is increasing into the coil. So the coil should produce a current so that the flux increase will not be there. It will maintain the same flux. So it will be anti-clockwise. Correct. Okay?
Yes, sir.
Yes, sir.
Resistance. I hope you are enjoying the problems. And this is how you should do. Now don't sit there and calculate. Some student may be sitting there and doing calculation. He will go to dogs. So don't waste time. Now we have to conserve the time and make the best use of time. Okay. 10 ohm resistance has coil of 10 ohms. It is placed in magnetic field of induction. So much a Tesla. 1 Tesla is what? 1 Weber per meter square. Correct now?
Yes, sir. Yes, sir.
Keep that in mind. So magnetic induction means B bar. Okay. For 1 second, it is placed in magnetic field of so and so Tesla for 1 second. If the area of the cross section is 1 meter, then calculate the induced EMF. Okay. Somebody can make the strategy here. Very simple. N is given here. Magnetic field is given here, and area is given. So B into A you get, and they are given you time. Delta T they have given. So B into A divided by time. Okay, so that is going to give you E, and E divided by and into 1000 you should do. Into 1000 you should do. Okay, so into 1000 you should do. So then you will get the induced EMF. What is the use of 10 ohm resistance there? It is not necessary. Okay, so I think 1000 into 5. So this is 10 to the power of 0.5. 0.5 upon 0.1 will give you 5. 5 into 1. So you should get here 5 volts.
5 volts.
You should get there 5 volts. Hello.
Yes, sir.
Serena, 5 volts, sir? Yes, 5 volts. Okay?
Yes, sir.
Okay. Now I think I have mixed up one more problem here. After that, so 5 volts. See, we calculated that orally. Fine. After that, there is a problem. Sorry, I have not split the problem. Can you read the problem? A coil of mean area 500 centimeters having 1000 turns held perpendicular to uniform field of 0.4 Gauss. The coil is turned through 180 degrees in 1/10 of a second. Calculate the average induced EMF. I hope you are able to read the sentence there.
Yes, sir.
Yes. So I hope all of you, we have already used this gauze and all the things, correct? Hello, I hope all of you know how to use that gauze and Weber.
Yes.
Weber per second. Okay. So what is the conversion? 10 to the power of minus 4. Multiply Gauss by 10 to the power of minus 4. You will get Weber. You will get the magnetic field in Weber per meter square. Got it?
Yes, sir. Yes.
Done.
Yes, sir.
So this also I think you can do it. See, they are asking you mean. Calculate the average induced EMF. So average means you should simply divide it by 2. Simply divide it by 2, or they are given some. They are given the time. Simply divide it by time. That's it. So area they have given, terms they have given. Area is in centimeter square. So 10 to the power of minus 4. So that gives you 5 into 10 to the power of minus 2. 1000. So that gives you 50. Then 0.4. 50 into 0.4. 5 4s are 20. 20. 10 to the power of minus 4. 20 into 10 to the power of minus 4. And the coil is turned through 180 degrees. Calculate the average induced EMF. So I hope you understood. No, the coil was like this. Now the coil is turned like this by 180 degrees. So they see, now if you take, this is the phase. This is the phase. The flux is entering from behind and coming out of this phase. Okay. Now if I turn the coil here, from this phase, the flux is entering. That means now relative to this, the flux has changed. That means the change is double.
Yes, sir.
Correct? That is change delta phi. Delta phi will be equal to phi minus of minus phi.
2 5.
Isn't it? 2 phi. Okay, so you will get here, you should get here 2 NBA. You will get 2 NBA divided by 1/10. That is n into 10. So 500 into 10 to the power of minus 4 into 10 into 1000. So that means now 500 will remain. Okay, and 500 into 0.4 into 10 to the power of minus 4. Okay, that will be the average induced EMF. So the change in the flux will be 2 NBA. That's it. That is important here. Divided by the time. Yes, 2 NBA. 2 NBA.
Yes, sir.
Correct. Whatever we did was right. Okay, friends.
Yes, sir.
Okay, see, you just get the final formula and write the things. See, here it is converted into 0.1 and all, don't do all these circles. So you simply write 1 by 10, things will become easier. Shown in the figure is a circular group of radius r and a resistance R, a variable magnetic field of induction. Here you see the magnetic field is variable. B naught e raised to minus t is established inside the coil. When the key is closed, then calculate the electric power developed after the key is closed. Fantastic problem. So if you have understood the theory, you will solve this. So what is the science behind this? If you explain correctly, then you will be able to solve this problem. Yesterday I already told you the theory for this. So radius is given, so you can get the area pi r square. B into A you will get. B is variable here. B itself is variable. So after the key is closed. So you will get the power in terms of this. Somebody who has got the strategy can come up and explain. Shall I solve? So, what is the strategy here? So you know that there is an area coil. Important thing is they are given B is equal to B naught e raised to minus t. Okay, and they are given the radius. So therefore, straight away we can write the flux linkage. Flux linkage is what? B into area. B into area will be pi r square. Hello, are you with me?
Yes, sir.
And here B is what? B naught e raised to minus t into pi r square. Okay, so this is the flux linkage, that is n phi. That's what we have got. And n here is equal to 1. Now they are asking power level. So if you differentiate this, you will get the induced EMF. So the induced EMF here will be, so V naught is constant, pi r square is also constant. So you differentiate this, you again get e raised to minus t into minus u minus u. Okay, correct?
Yes, sir. Yes, sir.
And already there was a minus, so minus minus becomes plus. So this is redundant. So you get the induced EMF here. Now this induced EMF, and they have given the resistance there. They have given the resistance, correct?
Yes.
So they are asking you after the key is pressed. Okay, so they are given a key here. They are given a key there, and when the key is closed, just after the key is closed. That means now, if we have to now say the key is closed, the key is closed at a time t is equal to 0. That is what it means. Key is closed means it is time t is equal to 0. Okay? Hello, are you with me?
Yes, sir.
So therefore the EMF at the time t is equal to 0 will be B naught pi r square e raised to 0 is 0. Correct? Sorry, e raised to 0 is 1. So this is what? This is the induced EMF at time t is equal to 0. Okay? Hello? This is the induced EMF. So then what is the power? Power is V square by R square. So the power that here will be equal to V naught pi R square by R. So this will be the power at time t is equal to 0. That is developed in the circuit. I hope we are right. Hello. I hope we are right.
V square by R, sir.
V square. So pi square r to the power of 4 by.
Yes, sir.
Thank you. So V naught square pi square r to the power of 4 by r. Okay, ठीक. So this should be the answer. Yes. This
Yes,
is the
sir.
answer. Okay. So see, please aram se. So now you know we have to strongly think this is science, this is it. Keep it strongly. We should not देख लेंगे बार कुछ लगा के देखेंगे क्या होता है ऐसा नहीं सोचने का. Then you are not learning anything. Okay, this is not Kaun Banega Crorepati, or we are not gambling here. Okay, you should be fairly confident and you should reason out like this is the reason why I am going to do like this. Okay, and then put it confidently. Confidently put it. Then you see the answer. If it is correct, be humble and say okay. But if it is not right, you be very happy. This concept I didn't understand. This is where I went wrong. Okay. Okay. Thank you God. Thank you Almighty. I have. I can now. I didn't know something. Now through this problem, I have understood my mistake. So you keep on correcting it. That itself is training. Okay. See, I am also solving in front of you. Okay. Two concentric coplanar circular loops made of wire resistance per unit length is so per unit length. Two concentric coplanar circles having different diameters. A time varying potential difference of so and so is applied to the larger loop. Calculate the current in the smaller loop. So you draw the diagram, then you will get the answer for this. So I think all of you should be able to solve this. I'm just showing you the key here. This is the key. This one has to close the key. Usually we do this. So they are given the diameter of this and they are given the diameter of this. Two concentric circles with same center. So two concentric coplanar circles made of wire and the resistance of each wire per unit length they are given. So have diameter so and so. The diameters are there and they are given resistance per unit length. So they are given resistance per unit length. So what will be the resistance of this? The resistance of this will be 2 pi d1 by 2 or pi d1 is the length into the resistance per unit length. Okay, of this one, not this one, of this one. And this one will be pi d2 r, the resistance of this. Then, okay, a time varying potential of so and so is applied to the larger loop. Find the current in the smaller loop. So here they are giving you time varying loop. That means they are giving you a time varying. What is the potential they have applied here? That is 4 plus 2.5 t. So 4 plus 2.5 is the voltage that they have applied. Hello friends, I hope the problem is represented. So what happens because of this? There will be current that will flow here. Correct? So just go by that. So what will be the current in the outer loop? The current in the outer loop will be 4 plus 2.5 t divided by pi d2 r. Okay, this will be the current in the outer loop. See, remember, this current is a function of time. This current is a function of time. Okay. Now they are asking you what is the EMF induced in the, calculate the current in the smaller loop. They are asking you what is the current in the inner loop. What is the current in the inner loop? That is what they are asking. Due to this, what is the current in the inner loop? So obviously the current is flowing here, so it will create magnetic field inside this. Okay. See, the current is going like this. The magnetic field will be created within this loop. It will also be outside, but what we want is inside the loop. And what is the magnetic flux linking? What is the magnetic field that is changing within this loop? That is precisely what you do. Okay?
Yes, sir.
So, How will you go about doing it? So try to use yesterday's Maxwell's equations. Will it be more useful? Do the way you want. But here they are told not told small loop and all. Correct? The loop is quite big. Okay, can you calculate the magnetic field at the center here? Due to this current I know, what will be the magnetic field at the center? See, you have done this now. If this current is I, what is the magnetic field at the center?
I by 2 pairs.
Huh? How much?
Yeah, not I by 2 pi.
Mu naught I by 2 pi r. Mu naught I by 2 pi r. Are you sure? Mu naught I by 2r, not 2 pi r. Hello?
Yes, sir.
Mu naught I by, see, I calculated, I derived it instantly. Mu naught I by 2 r. So here r will be d by 2. Isn't it? So r will be d by 2, so we will write it as d2 is the radius. That is the magnetic field at the center. Correct?
Yes, sir.
Now, but the magnetic field at these points are different. Hello? Correct now?
Yes, sir.
So therefore, how will you see, if it was same everywhere, it is different. But now the magnetic field at each point is different. The magnetic field at each of these points are different. You see, similar problem we have solved, but they had made our life simple by telling consider a small loop. Here the loop is not small. So you have to account for the magnetic field at each point. What will you do? So at some arbitrary distance x from this, what will be the magnetic field at this point? Magnetic field at this some arbitrary distance x. mu naught by 4 pi, okay, I naught into dl by x square. Hello, correct now?
Yes, sir.
So that will be the magnetic field at this point. So since the current is like this is concentric, you will get the same magnetic field here. Okay? So this will be the formulation. This will be the formulation for the magnetic field here, and the same magnetic field will be there throughout. Okay? Hello, are you with me?
Yes, sir.
Now this x, you write it in terms of, ulta. That is, from here to here, what is the distance? If this is x, because this total is d, so this becomes x will become what? If you take x from here instead of this, if you take x from here, okay. So because this distance is known, so you can get the formula for the magnetic field at this point, all these points, by using this formula. Correct? Hello?
Yes, sir. Yes.
This magnetic field into incremental area you take. What will be the incremental area here? 2 pi into this distance into this thickness. So that will give you the incremental area. That will give you the B into A, the flux in this region. Then you have to integrate it. You have to integrate it from 0 to this diameter. Then you will get the total flux. You got it?
Yes, sir.
So you have to do by that method and get the total flux, flux due to I naught. And now if you substitute for I naught itself is time varying, then you have to differentiate it into it. That's the way to handle this problem. Okay?
Yes, sir.
So you take down the data and try this problem. Tomorrow we will continue. I have stopped the class now at 9 o'clock because tomorrow is festival. We have to do a lot of preparations. So tomorrow we will have class. Hello. Tell me, everybody tell. See, I am giving you opportunity. I will not feel bad if you say don't want class tomorrow. It's up to you. I am not going to put it because it's a festival. It's a family function. So I don't want your family members to feel jittery. That is why, I am giving that concession. You can choose and tell me what time you want, how you want, etc., etc. I will do according to that. Or if you don't want the class, you say don't want. Okay, please. I want every student to enjoy learning. And I don't want family members to, scold you because of you alone. The whole family should not be in trouble. I don't want parents to feel bad.
Sir, please don't keep class tomorrow.
Why?
We have celebrations, sir, and we do Visarjan on the first day.
If you are doing Visarjan on the first day, you need, yes, I can understand. Okay, so we will not give class tomorrow. That I understand. That's why I asked. Some religious sentiments will be there, and that's why I asked. Okay, so tomorrow no class. So straight away we are meeting day after tomorrow. Okay?
Yes, sir.
Yes, sir.
Okay, good night. Enjoy.
Can you send more problems, sir? Remaining problems?
I will do that. That's a good suggestion. See, Aryan, I really appreciate. So what I will do, I will take out all the remaining problems and shoot it to you. You try and solve it tomorrow. Good. That's a good thinking. See, you all now be very, very enthusiastic. You move forward now. You start suggesting to me, sir, we'll do like this, sir, you take class, sir, don't take class, sir. Now, you use me to the maximum extent. You abstract all that knowledge, everything, whatever I have got. Okay, so you do it. That is what I want you to do. I want you to be now proactive. It's not one way. See, I go on doing whatever I feel is right. So I don't do. But maybe if you tweak, see now, do two good, very good suggestion from Aryan. Sir, you give all the problem tomorrow anyway. We are free. We will sit and solve. Wonderful. I will set the problems right away. Okay. Fine. Good night.